So in this module 13, we're going to talk a little bit about formal methods and object-oriented technology. I have a couple of slides on it. For this, you guys really need to go through chapters 15 and 16 of our textbook, very detailed. So this is definitely required reading material to go through these sections and read what's given there. In addition, I have uploaded a couple of other papers and tutorials regarding some of the aspects that I talk about in the slides on Blackboard that I would recommend you maybe not necessarily to go read completely through it, but at least look at it to give you a little bit more insight in formal methods, in certain formal methods, as well as some of the aspects or problems with object-oriented technology. So one thing is to realize that in the new D178C, there's two dedicated supplements, one dedicated to formal methods and the other dedicated to object-oriented technology. So we'll talk a little bit about it here. Well, if you look at formal methods, what we really try to do is two things. First thing is we're going to come up with a formal model of our system, or our subsystem, or our component, which is really kind of an abstract representation of that module. So that's like, to think about it as a mathematical representation of our activities or tasks that need to be performed by our particular subsystem. Then that abstract representation can be used to perform a formal analysis, which means I'm actually using mathematics and mathematical reasoning to actually guarantee that the properties are always satisfied by the formal model. So think about it this way. Actually, I'll talk about that on the next slide. So again, D178C has this supplement D0333 on formal methods, and that states that you can actually use formal methods in a very selective manner to partially address a small set of all the objectives. Remember the objectives from D178C. So an example would be, that's what I was going to talk about, if you, on your left, you see a set of high-level requirements that are written in plain English text. Well, it would be really hard to say to mathematically try to take these textual requirements and evaluate them in order to check out if this set of text is really implementing what it is we need to implement. Yeah. So what you could do is you can actually model this text by some kind of more abstract description language like given here. It almost looks like source code, but it isn't. And this notation here can be used much easier for an automatic tool to analyze certain mathematical aspects, or use mathematical tools to analyze these, in this case, three requirements that are given over here. So there's in typical three formal analysis techniques, at least that are mentioned in the formal methods supplement. One is the deductive methods, another one is model checking, and the third one is abstract interpretation. In the deductive methods, what you're trying to do is you try to specify a formal model, and then you're gonna say, well, I'm gonna mathematically somehow prove a particular property or a particular specification of this formal method. Okay. So then the correct proof of a property provides rigorous evidence that that property is present in this particular formal model. Okay. If you look at a couple of examples here in the US, you have, for example, PVS, which is the prototype verification system that was developed by and for NASA Langley. And I definitely recommend you to go to their library to find out more information about this. You have ACL2 and some European exams like Coq Isabelle and HOL, higher order logic. Yeah. An example of one of these, like a small little PVS example that I took from a PVS tutorial, is given over here. You see that in this particular case, you define a formal model, and it almost looks like some kind of programming language. You define it very formally, because then this can be interpreted by a computer that then can perform some kind of mathematical analysis on it. So I'm not going to go into too much detail. This is not a class on PVS, but here we define a with 2 lines a function that takes a phone book and a name and returns the phone number. So phone book and name returns the phone number. So we kind of describe this very formally, and then actually we're going to make a conjecture. If I add a name NM with phone number PN to a phone book and look up the name, I should get back the phone number PN. So now you can use your tool to find out if that really works. Yeah. Of course, this is a very simple example, and I definitely recommend you if you're really interested in PVS or any other deductive method to take a look at some of these examples. So another way is the model checking approach. In this case, again, you have a formal model, but what you're trying to do is you explore all possible behaviors, and this can be done by kind of exhausting evaluation of the formal logic that you have provided. And then in the cases where this property or a particular specification is not satisfied, you'll try to make sure that you can come up with a counterexample that illustrates where and how the property fails to hold. Yeah. So these model checking tools will do this more or less in an automatic fashion. The last one is abstract interpretation. Now here really we try to kind of come up with a kind of a conservative representation, which is also very formal, of the programming language semantics. And then we use that kind of formal representation to show certain properties or certain things that you intended to have in your program, like data flow, control flow, number of cycles it takes to execute, worst case execution time, etc., etc.